All right, today we're looking at 3.1, factors and multiples of whole numbers. This is section 3.1 in your textbook. So a prime number is a number that is only divisible by itself and 1. So some examples are 2, which seems odd because it's even, but it is only divisible by 2 and 1. Then the rest are all odd numbers because every other even number can be divisible by 2. So other examples are 2, 3, 5, 7, 11, 17, 19, 23, onwards and upwards from there. A composite number is a number that is composed of prime numbers. So 2 times 5 is 10. 5 times 7 is 35. We could also get examples like 2 times 2 times 5 times 7. It doesn't just have to be two prime numbers multiplied together. So 4 times 5 is 20, times 7 is 140. So every number that can be divided by basically anything else is a composite number. So write the numbers as a product of its prime factors. So what we do here is we divide until you cannot divide anymore. And we're just going to write out what we're dividing by each time. So 16 can be divided by a bunch of different things. We could do 8 and 2, we could do 4 and 4. We won't ever write 1 and 16 because I still have to divide 16. Okay, so leave 1 out of it. So I'm just going to choose 4 and 4. If you chose 2 and 8, we're going to get the same answer. So what this says is that 4 times 4 is still 16. All right. So we're going to keep going. 4 can be divided by 2 and 2. All right. So 2 times 2 is 4. Great. Same thing over here, 2 and 2. What I say is to circle the prime numbers. So what that says is any circled number, all of those multiplied together should still equal 16. So 2 times 2 times 2 times 2 is still 16. We'll write that 16 is equal to 2 times 2 times 2 times 2, which I can also write as 2 to the power of 4. Okay. Same thing over here for 4,200. Doesn't matter how you start it, we're going to get the same answer. So I did 42 and 100. So 42 times 100 is still 420. Dividing these, I get 6 and 7. 7 is a prime number, so I don't have to try and divide it anymore. I'm going to circle it. 100 is 10 and 10. Now, any number that's not circled at this point, we have to keep dividing. So 6 can be divided to 2 and 3. Both of these are prime numbers, so I'm going to circle them. 10 can be divided to 2 and 5 each time here. And each of those are prime numbers, so I'm going to circle them as well. So I can say that 4,200 is equal to 2 times 2 times 2. So I'm just putting them in order here. So 2, 2, and 2. And then next up would be our 3. We have 1 3. We have 2 5s and a 7. So a better way of writing this, I'm just going to move up here because I'm out of room, is 4200 is equal to 2 cubed times 3 to the power of 1, so I don't need to write the 1, times 5 squared times 7. Okay, the greatest common factor, or GCF, of 2 or more numbers is the greatest factors that the numbers have in common. So how we're going to do this is we're going to write the prime factorization of each number. Okay, so I'm just going to go ahead. So if we're looking at our two numbers here, 126 and 144, it's not really clear what the biggest number that both of these can be divided by is. So what we're going to do is we're going to write the prime factorization of each. So I'm just going to quickly do that, and it should just appear on your screen as one. All right, so if you take a moment and pause yours and do this as well, we should get the same answer. 126 is 2 times 3 squared times 7. Again, because there's two 3's, 3 times 3 is 3 squared. 144 comes out to 2 to the power of 4 times 3 to the power of 2. So the greatest common factor here is the maximum of each factor found in both numbers, if that's another way of thinking about it. So in 126 and 144, both have 2. The greatest number that they both have in common there is just 1, 2. So 2 to the power of 1. Then we're looking at the 3's. 126 has 3 squared. 144 also has 3 squared. So the greatest number of 3's I can take from both is 2. Now 126 also has a 7. 144 doesn't. So 7 doesn't appear in my greatest common factor. So greatest common factor will equal 2 to the power of 1 times 3 squared. So that would be 18. The lowest common multiple is the smallest common multiple of several numbers, okay? So you looked at that with your first activity, the beads, where you could just list it. So there's 2 methods of doing this. For small numbers, what we're going to do is we're just going to list the multiples until we see one that is identical between the 2, okay? For large numbers, we're going to do something different. So let's just start with a small number example. So the lowest common multiple of 4 and 6. I think that these are small enough numbers to work with, so I'm not going to do anything complicated. We're just going to do what we've done before. So I'm going to make a list for 8, 12, just counting by 4s here, 16, 20, 24. We could keep going, but I don't think we will. Then for 6, we get 6, 12, 18, 24, ... Now, I have to find the lowest multiple in both of these, and the lowest one is 12. Okay, therefore, the lowest common multiple of 4 and 6 is 12. Now, I've got a list of 3 numbers in this example. And not only do I have to make 3 counting lists of multiples, they're not really nice multiples. They're not small numbers, and I have no idea when I'm going to get to a lowest common multiple. So I would consider these large or more complex numbers. So what we're going to do is we're going to write the prime factorization for each. So pause the video and factor each of these down to their prime numbers. Okay, so we should get the same prime factors regardless of how you have divided these. So what we're going to do to find the lowest common multiple, we need to find a list of the greatest factor for each prime number. So what I mean by that is we're going to look at all of them and we're going to decide, we're going to keep every factor and we're just going to pick the biggest one or the biggest power for each, if you will. Okay, so we're going to start. I see 2 as a first factor in both 28 and 42. It doesn't appear in 63, but I'm picking every factor that I'm seeing. So if you want to get started by this, you can even say the lowest common multiple is equal to. We're going to have 2 to the power of some number because 2 exists in these. I'm going to have 3 to the power of some number because it exists. And I'm going to have 7 to the power of some number because it exists in all of these. Or in 1 even. Okay, so I'm looking at the 2's. I've got 2 to the power of 2, 2 to the power of 1, and no 2 here. So the largest power is 2 to the power of 2, and that's what I'm going to say my answer needs to be. My lowest common multiple is 2 to the power of 2. Okay, next one, I'm looking at my 3's. 3 doesn't appear in 28's. Factor. It does appear as a power of 1 in 42's factor, and it appears as a power of 2 in 63. Therefore, the greatest power is 2. And 7 appears in everybody's factor, always to the power of 1, so the greatest power is to the power of 1. All right, this means that my final answer will be 2 to the power of 2, which is 4, times 3 to the power of 2, which is 9, times 7, and I did that in my calculator and I got 252. All right, so we take basically every number, every prime factor, and we see the biggest one that exists in some number, and we place it in our lowest common multiple, multiply it out. If you're not convinced, go ahead and make a list. Count by 28, by 42, and by 63 until you get to 252. And I guarantee that there will be no other number that you hit first that they all three have in common. All right, a contractor sees that he has extra tiles left over from a previous tiling job. What is the side length of the smallest square that could be tiled with the rectangles that measures 8 inches by 36 inches? So the tiles are 8 by 36, and we want to use those tiles to make a big, the smallest square possible. All right, so assume that we cannot cut tiles, and we're going to sketch this in the end. So smallest should be your cue that we are looking for the lowest common multiple between 8 and 36. Okay, so we can make a list, or we can use our prime factors and find the lowest common multiple that way. I'm going to do prime factors because I think that often it is the trickiest for kids, and so we'll do it that way. I'm just going to make my factor tree here. Pause your video and do the same. All right, so I factored. I've got that 8 is 2 to the power of 3, and 36 is 2 to the power of 2 times 3 to the power of 2. Sorry, it's not perfect with my stylus and iPad here. All right, a lowest common multiple. I know that I have factors of 2 and 3, and I just need to decide what power I need to do. So 2 is to the power of 3 here, to the power of 2 here. The greatest power is 3, therefore my lowest common multiple will be 2 to the power of 3. I don't have a 3 in 8's factor, but I do have a 3 over here. The largest power then is 2. So my lowest common multiple will be 2 to the power of 3, which is 8, times 9, and that is 72. So if I were to draw this, I'd make a square, my perfect square, that is 72, okay? That means if my tiles are 8 inches, to get to 72, I needed 9 tiles, 2, 3, 4, 5, 6, 7, 8, 9. 9 tiles, 9 rows, of tiles, and each tile again was 8 inches. This whole side would be 72, inches. And then the tiles are 36 inches, so I need it 2 tiles wide, where this is 36 inches, and the whole side length again is 72. All right. So the second piece of this is, what is the side length of the largest square that could be used to tile a rectangle that measures 8 by 36 inches. So now we don't know the size of our tiles, we do know the size of our space. Okay, so we have this space that is 6 inches and 8 inches. And we want to find the biggest tile that is square that could fit in there. Okay, so we're looking for the largest, meaning the greatest, therefore it is the greatest common factor. Okay, these keywords help us to identify what we're looking for. So it's the largest divisor of both 36 and 8. So again, 8 was 2 to the power of 3, and 36 was 2 to the power of 2 times 3 squared. The greatest common factor that they have in common, well, the only factor they have in common is 2. What they have in common, the greatest number of 2's that they both have is 2 squared. Therefore, our greatest common factor is 4. That means I can divide, my tiles need to be 4 inches by 4 inches. And I'm going to divide this. These don't look like squares at all. I did my best, but these would be square tiles, 4 inches by 4 inches. Okay, reduce using the greatest common factor. So we've reduced fractions before. We would just go by a trial and error, or what are they both divisible by. But if we go ahead and factor both of these numbers, we can use their factorization to do this. So go ahead and make that prime factor tree. Okay, so I've gone and factored, and I'm just going to write them out as our regular factors. I'm not going to put them to the power. I'm going to write them out as many times as they existed, just for this example to show what's going on. So 216 is equal to 2 times 2 times 2 times 3 times 3 times 3. All right, and 264 is 2 times 2 times 2 times 3 times 11. So what we're looking for here is numbers that we can cancel both top and bottom. So I can cancel these 3 2's because they exist in both the numerator and denominator of our fraction. I can cancel 1, 3, and that's it, because in the top of our fraction right now, we have 2 3's, and in the bottom, we have an 11. We can't cancel those. Therefore, my final answer is 3 times 3 over 11, which is 9 over 11. Evaluate by finding the lowest common multiple. So lowest common multiple, again, I can either write out a list of multiples until I find one that's the same, or I could factor and use that to find the lowest common multiple. Because 4 and 16 are pretty small, and I think we all know what the lowest common multiple is just off the top of our head, I'm just going to make a list. So 4, 8, 12, 16, voila! I don't even have to list 16's multiples. The lowest common multiple is 16 itself. To get 4 to 16, I need to multiply by 4. Whatever I do to the top of a fraction, I do to the bottom. And the reason being, 4 divided by 4 is just like multiplying by 1. So I haven't changed it at all. So I can say that this statement is still the same. So they are equal. And it is 28 over 16 plus 9 over 16. So we get 37 over 16 as a whole fraction. I could write it as a mixed number if I wanted to, and that could be 2 and 5/16. Whatever you wrote, that would be fine. All right, the prime factorization of 2,646. You would make a factor tree here, so pause and go for it. In the end, you should get that 2,646 is equal to 2 to the power of 1. I don't write the 1. Times 3 squared times 7 squared. At this point, you can go back to your demand line and do the homework for this topic. Get some practice in because we're going to need it in the long run here.